this is the stage I left you this morning with a resolvent that we solved for in terms of kappa. And now, to simplify things, I will set lambda 1 equals lambda 2 equals lambda, and 1 equals n2 equals n. And I told you that this is somehow an implicit solution because it's all in terms, the resolvent is given in terms of kappa. Here's an f here. And the number of eigenvalues for the Atoll coupling is then given implicitly by the integral of it. So has anybody calculated this integral during Koya's talks?
Captain Billy.
Sorry?
Captain Billy.
Okay, anybody want to calculate the integral now? Do you know how to integrate a log of a square root of a quadratic? No? Okay. If you don't know, what do you do? If you don't know how to calculate an integral?
Use mathematics.
Yes. Mathematics cannot do it. Next. You differentiate. So what we calculate is the derivative of lambda. It's actually total derivative in this case. Because the nice thing is that it gets rid of this logarithm. So this will be equal to, if I did things correctly, pi over 8 pi squared. I'm not completely sure about these numbers. We need to do it correctly. So here you get the square root of this. So I think this is exactly it, and all these other terms miraculously cancel themselves. And now can you do this integral? So now you go to the previous solution. You use Mathematica. So this is an elliptic integral. This is actually the simplest elliptic integral possible. No complications in front of this square root here. And you're integrating around a closed contour, which tells you it's going to be twice a complete elliptic integral. So this is equal to 1 over 4 pi squared capital K. So that's the complete F integral. Pi kappa over 4. So kappa is of course related to A and B, as I wrote before, and this is the complete elliptic integral. Now, I had the question before of how do I know the structure of the cuts exactly, and it is indeed not the way I wrote it. So I have branch points here and here, and branch points here and here, and the cuts are actually here and here. And this is, I think this is the C1 cycle, and this is the C2 cycle. But this doesn't really matter at this. I mean, you can be careful about keeping track of these things, but at the end what you can do is just calculate the different cycles. These are all going to be different complete elliptic integrals of this guy, or the complementary modulus, and so on. So once you know what the elliptic modulus of this elliptic curve is, you can find what are all the period integrals, and these will be the different integrals you can calculate, and then you check which of them has the correct asymptotics. For small kappa, it behaves like 1. You expect kappa to be equal to lambda. You can see it from the original definitions. So I hope you're not afraid of of elliptic integrals, because now we need to integrate them. So lambda of kappa, this turns out to be equal to kappa over 8 pi 3f2. So this is a hypergeometric function. So this is the answer. It's in the books, and I think also Mathematica knows this integral. And you shouldn't be afraid of elliptic integrals or hypergeometric functions, because as we learned this morning, the most complicated function is a square root, and these are simpler. So now we have an explicit map of kappa to lambda. Actually, our curve is given in terms of kappa. Lambda is the 't Hooft coupling of the theory. So what we need to do is invert this relation and get kappa in terms of lambda. This function does not have a name, but lambda as a function of kappa turns out to have a name, so we will leave it in this form. And you can invert it numerically or perturbatively or any other way. In particular, I will tell you what you find if you study the asymptotics of this function for large kappa. The asymptotics is that lambda of kappa is equal to log squared of kappa divided by 2 pi squared plus 1 over 24 plus log of 1 over kappa squared. So you find that kappa behaves like e to the pi square root of 2 lambda minus 1 over 24. And you can call this lambda tilde. This is an effective 't Hooft coupling and strong coupling. When the 't Hooft coupling is large, the effective description, the effective coupling is lambda minus 1 over 24 instead of lambda. And there is an explanation for it in terms of, in string theory, you can see that there is a shift in the radius of curvature of ADS, and the radius of curvature is related to lambda. So we got the kappa as a function of lambda implicit as the solution of this, or that strong coupling explicit like this, and then you have a series of corrections to it, which you can calculate to whichever degree you would want. So this is nice, and we solved the matrix model, and Kolya will use this F tomorrow. Okay, good. But what else can we do with this? So, any ideas? What you would want to calculate? What would you want to do? No. Anything you want to do apart from the lake? Ignore the lake. Anything to do now?
Barbecue.
Barbecue, yes. The barbecue, you'll need to wait. The dots, you can do that. Yes. Sorry? Okay, so we have a few things we can do still with this matrix model. And the first thing we need to ask is, what do we get for the same price? So we did a calculation, and can we get something more without doing any more calculations? So there are some nice things that we can do. And one thing is, if we go back to ABJM theory, we may want to calculate another observable apart for the sphere partition function, and that is, we can calculate the expectation value of a Wilson loop. And a Wilson loop is given as something like trace, path-ordered, exponential, integral of IA, and then to make it supersymmetric, and to make it supersymmetric, you need to add a scalar piece, so something proportional to sigma. So this is a generic kind of BPS Wilson loop in Chern-Simons matter theory, in a three-dimensional theory, and it will preserve half of the supersymmetry of your theory if your theory has n equals 2. In the case of ABJM, if A is remember ABJM has two gauge groups, and so if I just include a Wilson loop in one of the gauge groups, that will not preserve half of the supersymmetry, or preserve only 1/6. There is a way to get it to preserve half of the supersymmetry, but I will not write it down. What I will tell you is that you can evaluate this in the matrix model. So this is consistent with the supersymmetry that we have there. And remember that when we localize, we had that A was equal to 0 and sigma was equal to sigma naught. So W will then become a trace path ordered won't matter because sigma is constant. So we're going to have sum I equals 1 to n e to the 2 pi sigma I. And this is what we will need to insert into this matrix integral that we had. We had this matrix integral with the cinches and the coches. If we want to calculate the Wilson loop, we will also need to insert this guy. And actually, this is the 1/6 BPS Wilson loop. The 1/2 BPS Wilson loop is just going to be the sum I equals 1 to n1 e to the 2 pi sigma I plus, actually I'm not sure if it's plus or minus, I don't remember. pi equals 1 to n 2 e to the 2 pi sigma I. So you need to include both eigenvalues, and then you get a half BPS Wilson loop. I will not write down what is the gauge theory version of it, which is very complicated. But as I told you, like in the case, the theory itself, we didn't really need to know what is the superpotential to write down the NICE for ABJM. When we localize, here too, it doesn't really matter. I can just add this gauge group and the other gauge group, and I will get something that is equivalent to the half BPS matrix model. So now, can we calculate this in the using our solution for the planar matrix model?
Sorry.
Yes.
In ABJM, N1 and N2 are equal.
They are. Yes. So I took them here to be equal, but a lot of what I say can be done with them not equal. Let's take them to be equal. So what I need to calculate here is a sum of the exponent of sigma around one of the cuts. So the expectation value of W16 will be equal to the integral around C1 up to some normalization, which I will not write down, dz e to the 2 pi z, and then a omega. So instead of calculating this, which gave me lambda, the expectation value of the Wilson loop will be given by integrating omega with this measure, which is actually just the integral dz, capital Z was this thing. So if I use this measure to integrate omega, I will get the expectation value of the Wilson loop, of the 1/6 BPS Wilson loop. The 1/2 BPS Wilson loop is even simpler. That is the integral over C1 plus C2 of the same thing. And if I go around both cycles, and here the sign matters, so I really go around both cycles, this is equal to 1 over 2 pi integral around infinity. So I can deform the integral around infinity omega, and now convince yourself that this is actually equal to kappa. So kappa, which appeared as a parameter in our curve, our solution to the curve, is actually it governs the asymptotic of omega at infinity. Infinity omega will go like kappa times z. So this integral will give us kappa, and we have its value, the expectation value of the Wilson loop is e to the pi square root of 2 lambda tilde. And this indeed agrees with the calculation using ADS4. String theory on ADS4 times CP3, which is the ADS dual, the holographic dual of the ABJ model. So these were, and you can actually calculate this, guys, the two 160 PS1 for the two different cycles. You can also calculate them, and they will be given by different elliptic integrals. And you can do that as exactly as you wish. So that is one nice thing that we can do. Another thing that we can do is look at other periods. So we can look at the different period, which is this. We're still at the planar limit. Yes. You can also go beyond the planar limit, but I will not discuss it. Yes.
Can you do correlation functions of multiple Wilson?
So I can do correlation function of Wilson loops that are consistent with supersymmetry. So I told you in order to do the localization, we had this symmetry on S3 of translation along the psi direction, the half fiber. So you can consider any number of Wilson loops that are half-linked. You can consider a Wilson loop in a higher dimensional representation. They're actually all going to be the same. It's just the number. We're just going to have a multiplicity. Essentially, you're going to calculate an integral z to some number. And this will tell you some kind of multiplicity for the Wilson loop, and then you can decompose it into different representations. So we calculate one period. The question is, now we can for the same price calculate a different period. And the question is, what does that give us? So normally in a matrix model, if I have here a cut, I can do the integral from infinity to the endpoint of the cut. That's an actual quantity. Do you know what this will calculate for you? So remember that omega was somehow the potential felt by an eigenvalue in this matrix model. So what you're integrating here is the potential from infinity to the cut. So it's as if you're adding one eigenvalue to your model, and you're asking what is the and you pay for it by energy. You're integrating the force over the distance that you did it. So this calculates the change of the free energy of the theory when you change the number of eigenvalues. So normally, integral from infinity to the cut of omega z is equal to the change of the free energy with the number of eigenvalues. So, where the partition function is equal to e to the minus n. Now in this case things are slightly different because we have two cuts. And we said that if we calculate, so this is what Collier corrected before, if we calculate it around here, we will get n. If we calculate it around here, we get minus n. So we actually don't have any eigenvalues in our problem. The total number of eigenvalues are 0, we have here particles and we have here holes. And if we want to change n, we need to move an extra eigenvalue from here to here. Or if I want to do it like that, from here to here. So the change, so if I move an eigenvalue from here to here, which is equal to the integral along the d cycle, so there is a half if I do it, but let's not worry now about numerical factors exactly. If I do the integral around the d cycle of omega, then this will be effectively the change of f with lambda, which is proportional to n. So the correct expression is there is an I, and there is a k squared. I think this is the expression. Yes. This is the expression. There is actually a constant shift to it. There is actually an extra term that appears in this, which is a little bit hard to find. I squared. So only there is when lambda 1 is different from lambda 2, there is an extra term. Otherwise, this is exact. So when lambda 1 is different from lambda 2, then you might worry about bringing extra eigenvalues from infinity or something like that. But when lambda 1 is equal to lambda 2, really all the eigenvalues just come from moving them from one cut to the other. So the complete change of the dependence of the free energy with n is given by this integral around this cycle. So this is this free energy, and now we can calculate it again in the same way by differentiating it again. So d squared f d lambda squared, that will be an integral of the derivative of omega, which we can calculate in terms of elliptic integrals. And this is essentially minus k squared pi k prime of I kappa over 4 over k of I kappa over 4, where k prime k is equal to k of squared. And this expression is exact, and now you need to integrate it. So I should tell you this is for large kappa. This is equal to minus k squared over 2. There's a pi squared. upstairs, and there's a log kappa. Downstairs, log kappa is square root of lambda, so we get minus k squared pi over square root of lambda to the 3/2, and we can immediately integrate it. F prime is equal to minus k squared pi over square root of 2 square root of lambda. F is equal to minus k squared pi square root of 2 over 3 lambda to the 3/2, and we can also write this as minus pi square root of 2 over 3 and to the 3/2 square root of k.
But in principle, what you're doing, you're computing action on the saddle point. If you can just integrate the action, that's just a trick to avoid it.
Yes. So this is the free energy, or the action evaluated on the saddle points, and it has this behavior that it scales like n to the 3/2 at large n, which is a feature of M2 branes. So normally, if you have a gauge theory, you would expect n squared degrees of freedom. So actually, I didn't worry here about integration constants. I'm integrating here. There is actually here plus n squared times lambda to the 0 degrees of freedom that you find in perturbation theory. At lowest order, it's just a number of degrees of freedom. But so there is a term that is larger in n, but it doesn't scale at all with lambda. Okay. So this is not the important behavior at large that you will see from supergravity. So this is all I wanted to show about the matrix model. This is all that you can get out of the planar solution of the matrix model. You can find all these corrections, and there is a clear interpretation of them in terms of worldsheet instantons, so you can understand them in terms of strings wrapping different cycles inside CP3, and other terms correspond to D2 branes wrapping cycles inside CP3, and then you can go to higher orders in beyond the planar approximation. But let me show you how you match this with the supergravity calculation, and I'll just end with that. So let us consider supergravity. On alias for cross S7 wants the K. So this is the M-theory description of this model, but one can also do the type 2A description of alias 4 times CP3. First, are there any more questions about the matrix model before I go to supergravity?
May I ask a question?
Yes,
You mentioned that there will be contributions from row sheet instantly.
yes.
Are they visible in the strict planar limit? Or they are suppressed by another?
They're suppressed by lambda, they're not suppressed by n. So they are visible in the planar limit. Okay. So this is the difference. So this is the exact answer in the planar limit. And if you invert this, you find this plus corrections which are it's e to the minus square root of lambda times something. And this is interpreted whenever you have square root of lambda, that corresponds to a classical string configuration, and the coefficient in front would be the volume of the cycle this string wraps. And then there are terms that behave like e to the k square root of lambda, I think. And this is the action of a d-brane. And these terms, many of so there's a big series of these kinds of corrections, and the numbers that appear here have been understood in terms of some topological invariance of CP3. This is essentially telling you the number of cycles or the dimension of space of these cycles. So let me take the metric will be equal to L squared d rho squared plus sinh squared rho d omega 3 squared and plus L squared S7 but actually let me work in a four-dimensional formulation, so I do the Kaluza-Klein reduction on this, and I just have the four-dimensional space, and the action in 4 dimensions will be equal to minus 1 over 16 pi g Newton integral d4x square root of g times r minus 2 lambda. So we have the Einstein-Hilbert action and the cosmological constant term. And you can view this. So of course, well, this cosmological constant term, you need it, otherwise you're not going to have an ADS solution. If you start from M theory, then you know that this term is going to come from this. So in M theory, you don't have a cosmological constant, but once you include the contribution from this term, this will give you effectively cosmological constant on the remaining part of space. But we are looking at it, we can write down the equations of motion, but we know what is the solution that we want. The solution that we want is this ADS4 space. It is a solution to the space with and in particular, we know what is the scalar curvature of ADS4 in terms of L squared, and we know how the cosmological constant will be expressed in terms of it. So this will end up being as classical evaluated on this ADS4 solution. This is going to be this goes from there. It's going to be 3/8 pi gn L squared times a integral for x square root of g. So r minus 2 lambda will effectively be equal to the ratio of this. It's 6 over L squared or something like that. The term that the ratio between here and this is the number. This you can read off because this ADS4 will be a solution to this action.
So once again, what is a lambda? How is it fixed? So it's fixed. Why?
Lambda, the cosmological constant.
Yes.
So the cosmological constant comes from the radius of S7. And the way you can view it here is start with this theory and fix lambda. Okay? Lambda is now, so now you have a four-dimensional theory with a cosmological constant. It will have an ADS solution. This radius of ADS will be fixed by the cosmological constant. So lambda is proportional to 1 over L squared. And this proportionality constant is the thing that appears here. So R is proportional to 1 over L squared, but L is proportional to lambda. So I'm starting here with L, but you should, if you solve the equations honestly, you should start as if you have a fixed lambda, then L is given in terms of lambda, and R is given in terms of L, and they're all proportional to each other, just giving this factor in front. So there is a unique radius of ADS solution given lambda. So these all are different. Did I answer your question?
Mm-hmm.
So we just need to calculate this area. So this is 3 over 8 pi gn L squared. And now integral. So, we need the volume of S3. Anybody remember the volume of S3? 2 pi squared, good. S4? I don't remember either. S2? Wikipedia has a formula. Always I get confused about what is the value of n there, n or n plus 1, but otherwise you can always view it there, find it there. So we have integral d rho sinh cubed rho, and this is equal to 3/4 pi. Oh, there was another L to the 4th here. L squared over g Newton, and now you need to integrate this. Mathematica knows how to do it, but you can also do it by hand. It's not very hard. It's 1/3 cos rho sinh squared rho minus 2 cos rho evaluated between 0 and some cutoff rho naught. So this is pi L squared over 4 g Newton, and now cos rho naught sinh squared rho naught minus 2 cos rho naught plus 2. So now you need to be careful about these divergences, and you need to add counter terms to your action. So there are all kinds of counter terms you need to add to your action. The most standard one is the given popping term, because R is a total derivative and it has a natural boundary completion, but that actually doesn't make it finite. There are other terms that you need to add, and there is this whole theory of holographic renormalization and what are the possible counter terms that you should add. But if you're practically minded, you're just going to do this. And this, you do have to be careful, because nobody guarantees that the counter terms are not going to be finite. And if you come to my talk on Wednesday next week, there is a boundary term which is finite. But today there isn't. So we get pi r squared over 2gn, and this is the answer, except that we need to write it in terms of so this is the answer if we know what L squared is and what the Newton constant is, and that's completely fine, but then we need to translate it to gauge theory observables, N and K, and there are different ways to do this. The simplest one is to open the Aharoni, Bergman, Jeffries Modesina paper, and they tell you exactly what is the dictionary between ABJM variables and supergravity variables. You can read it off by knowing what is the flux, what are the fluxes, and the fluxes play the roles of the cosmological constant and so on, and the fluxes are always the things that are quantized. They're going to be giving you this K and N parameters. But essentially, G Newton at the end is equal to 3 square root of 3 over 2 square root of 2. Then you have here pi squared n to the 3/2. And upstairs you have the volume of S7 mod zk. Quickly calculate the volume of S7 and an L squared. S7, anybody knows the volume? So that's the answer. And this gives you 3 over 2 square root of 2. L squared over n to the 3/2 square root of k. Yes, that's a question?
The range of S7 over the 3 is not k.
It's L over 2 or something like that. Yes. Either 2L or L over 2.
It should be factor because it's ADS 4 versus 7.
Yes.
It's a relative factor.
Yes, so the relative factor of 2, yes. So if we plug this in, we get that S is equal to square root of 2 pi over 3 n to the 3/2 square root of k, and hopefully it's the same as we had there. So the free energy of the matrix model is minus the action of supergravity, so the partition function of supergravity e to the minus s is f, and maybe I have the sign wrong somewhere. But this is the agreement between supergravity and the action of the matrix model. So I'm a few minutes early, but I think.
But what about the finite contour term is that then it will break the relation.
Which finite term?
You said today that there is no finite term, but during your talk, the class, there is some finite term, you change the answer. What was that about?
Finite term, do you mean the n squared there?
When you cancel this cautious,
The thing you crossed out, regularization term.
This term?
Yes.
you said
This is not finite.
yeah, but you said there will be some finite next.
There will be finite term that will give me the correct number here. So there I use a different action, a different bulk action. I add more matter fields. It's not just gravity. It's gravity coupled to vector fields. And if you calculate the contribution of the gravity coupled to the vector field, you get a different answer for the finite piece. And then you need to argue that there's a different boundary term because you're working on different formalism. And then better give you the same answer. And then it doesn't. If you close your eyes and wish for the best, you do get the same answer. But it's because the bulk action there is very, very different. And also the boundary action is different. But you can worry about that term, for example, but this you won't see in this approximation. This approximation only captures this leading term, and for that you need to get more terms beyond this. You need to somehow do quantum gravity, which is what I will talk about on Wednesday. So actually you can calculate the corrections, the 1 over n corrections to this, which comes from graviton loops, effectively. And the way we try to capture them is by considering this funny supergravity coupled to vector fields in ADS4 and localize that. So if you localize gravity, you get an exact result in gravity to all orders in 1 over n.
So it's 1 over n times square root of k. Or just 1 over n. And then the formula there,
Sorry?
on the upper board,
That one?
yeah. What's the thing?
I'm not sure. I haven't checked what this formula gives at weak coupling, whether it gives the n squared or not. I can check that. So this is actually the exact answer that we find is an airy function of n minus this 1 over 24 k over 24 plus 1 over 3k, and then some number in front of this square root of 2 pi over 3 to the 2/3, and then some number in front of here, and this you can check what that is equal to at when n goes to 0. Whether it gives the same as that, I don't know. Any other questions?
For a BJ theory, what is this relation between number and the coupling?
I don't remember off the top of my head. I think That's not integrable. So why do you care? And
Now there were those claims of right? Recently that you can just replace sublime and it will be the same, just replace coupling, be happy.
You can do everything, but I think the explicit formulas get even nastier. These. I don't remember if there is an effective, the average lambda or something like that is still given by explicit formula. I don't, as far as I remember, it's not, but I'll have to relook.